Yeah, so in some sense, it's not really a continuation of the talk of Corentin Audiard this morning, but I think it fits very nicely. And yeah, lots of the structure he showed in the beginning of the talk will also show up in the beginning of my talk. But in some sense, the viewpoints we have, I would say, are in some sense orthogonal, because he was mainly talking about existence and I'm mainly talking about stability. So I think that fits very, very nicely. Okay, so I'll start with an introduction, and actually in the case I'm looking at somehow what is mathematically called an entropy from the physical viewpoint, de facto an energy, so I tend to call it relative energy, and when I was preparing the talk I was struggling with making it uniform, so I somehow put this slash. It will essentially mean the same thing during the talk. And once we've established what relative energy or entropy is and what we can do with it, I'd like to show two applications, and one is really, I would say, an applied analysis application, which is studying the large friction limit of Euler-Korteweg. And yeah, in the last years I've done a lot of numerical analysis, and I'd like to also highlight how these stability results, as this one, can be used in the analysis of numerical schemes. Okay, so the starting point was, I mean, this is joint work, I should say, with Athanasios Tzavaras from KAUST and Corrado Lattanzio from L'Aquila. And somehow Thanos suggested to study rather general abstract settings in this form, that we have conservation of mass. And we have an evolution equation for velocity, and somehow here we see the material derivative we already saw several times today. And somehow this is driven by the gradient of some directional derivative of an energy functional. Okay, and once we have this structure, we can define a Hamiltonian, which, I mean, we've seen this morning and also this afternoon. And I mean, this was explained much better than I can explain it, so I'll leave it at the explanation which is here. So we have a combination of the potential energy and the kinetic energy in the Hamiltonian. And we can rephrase these equations, but it's not really a Hamiltonian system, because I mean, we have this first part here, and this because divergence and gradient are adjoint to each other, are anti-adjoint to each other. This is really an anti-self-adjoint operator, so this part is really Hamiltonian. But we also have this other part flying around here, which is a bit strange. It only appears in multi-D. It only appears if it's not curl-free flow, if there is a curl in the flow. But de facto, because in checking for energy conservation, this equation is multiplied by velocities, this doesn't really show up in any energy conservation equations. And I mean, this seems to be well known for a long time. I mean, there's certainly a paper by Raphael Danchin and Sylvie Benzoni, where this is already used in the early 2000s. But I'm not claiming this is the first time, so probably we have people in the audience who know better where this comes from. Okay, and at least formally, as I said, I mean, this doesn't really matter for energy conservation, so this Hamiltonian is conserved. Okay, and I want to have a little bit more of structure, and what I want to have more is the existence of a stress tensor. So I want, or I postulate, that there is this tensor S, so that the divergence of S actually matches minus density times gradient of the potential energy functional. And if this is the case, then we can actually rewrite the evolution equation for the velocity using the momentum, using the mass conservation as a conservation equation for momentum. And this is nice in the sense that we expect that physical systems display conservation of momentum, and in some sense the existence of a stress tensor should be a consequence of the fact that there is a translation invariance of the energy, and then we have Noether's theorem, which tells us that there is an additional conserved quantity. So this, I would say, is fairly clean for things like the Euler equations. It's also fairly clean for Euler-Korteweg. I have to say it's not so clear to me if we look at non-local energy. So I think it's still the case, but at least I'm not able to do the mathematics, but it's more a technical limitation of me than I think really something which is going on. Okay, and once we have this formulation, we can start talking about weak solutions. In particular, we can at least throw one of the derivatives onto test functions, and well, okay, it depends a little bit on what the stress is, but in some sense we can think about rather irregular solutions. Okay, so the easiest example I would say fitting into this framework would be the isentropic or the isothermal Euler equation. So the situation where the potential energy function is just the integral of some function of the density integrated. And typical examples would be rho log rho in the isothermal case, and rho to the gamma with gamma larger than 1 in the isentropic case. Then this variational derivative is nothing but the standard derivative of h prime of rho. And in the conservative form, the pressure shows up. So I mean, this is nothing but the compressible Euler equations in the isothermal or isentropic case, and the pressure is given by this, which is called Gibbs-Duhem equation. What I would like to stress at this point actually is that if we take the derivative of the pressure with respect to the density on the left-hand side, on the right-hand side we get rho times the second derivative of h. So some monotonicity of the pressure and convexity of the energy functional are very much related. So when we talk about non-monotone pressures, as I did talk about in the title, then this in some sense means non-convex energy densities. Of course, these two classical energy densities are convex, but later on we will see non-convex energy densities. Okay, another example which we already saw this morning are the Euler-Korteweg equations. So here we have a kind of local part of the energy density, and we have this gradient part, which depending on which way you phrase things, you can think of, well, it's not so clear whether you should call this local or non-local. And as we saw this morning, it's connected to the Schrödinger equations via the Madelung transform. Okay, in this particular case, the variation of the energy looks like this. So I assume here that kappa is constant. We can also deal with the case that kappa is a non-constant. Then all the formulas get longer, so I prefer to stick with the reasonably simple case. So you could argue that the stress is already pretty long. Okay, and for the stress, I would like to stress that we can do integration by parts here, and then we actually see that when we try to formulate, when we try to define weak solutions, we can actually do integration by parts once more here and throw things on the test function so that we can actually live with weak solutions which are which have one weak derivative but which don't have to have two weak derivatives. Okay. Another remark would be that, as I said before, we can treat the case that the capillarity coefficient kappa, which was k this morning, is dependent on the density. Then we need that it's positive. I mean, we always need that it's positive, and we need this additional condition, and this condition is in particular satisfied for the quantum hydrodynamics case, which is kappa of rho is 1 over rho. Okay. That's the problem if I use French computers. I have no idea what it says. Okay. Another example fitting into this framework would be the Euler-Poisson equations. So the idea is that you have a mass which is interacting via a potential field, and this can be either gravitation or electric forces. And the question of which one it is, whether it's repulsive or attractive, depends on the sign here, essentially. In any case, we have an energy density, and now in this energy density we don't only have dependence on rho. I mean, we essentially have dependence on rho, but this comes in via this non-local field C, which is given by an elliptic equation which has rho on the right-hand side. But of course you can use the Green's function and write this as a convolution of rho with the Green's function. Okay, and you can also write the stress, and now the stress is also non-local in the sense that the stress at a given point does not only depend on rho and its derivative at this point, but it also depends on C and the gradients of C on that point. Okay, so now we have this framework. There are apparently examples in the framework, but what do we really want to do? So what we want to do is we want to come up with the relative entropy framework, and this is something which has been around for a long time in hyperbolic conservation law. So now I would like to go to the Euler equation, so to the kind of hyperbolic standard example, and explain what relative entropy is for the Euler equations, and then the goal will be to extend that framework to these more general systems. Okay, so the Euler equations we can write using a vector q, which contains density and momentum density, and the mass flux and the momentum flux, and then they can be written in this first order conservative form. Okay, such a system is called hyperbolic if in all directions the Jacobian of f has only real eigenvalues, and if there is a full set of eigenvectors. That's indeed the case here. And as we've already heard this morning, these equations have a tendency to form shocks. And it's very, very easy to check that if there is a discontinuity in the solution, weak solutions are non-unique. So the question arises, which weak solutions should we pick? And one fairly obvious criterion is to enforce that the solutions are compatible with the second law of thermodynamics, and this brings us to entropy. So what we look at are pairs eta and mu, of which we call entropy and entropy flux, which satisfy this compatibility condition with the convective flux F. And if this condition for the Jacobians is satisfied, then we can simply multiply the equation with the q derivative of eta. Then this becomes the time derivative of eta of q. Here we use the chain rule, so we have dq of eta, then we have chain rule, so we have a dq of f times the gradient of q. We can combine this to a dq of mu times gradient of q. So for strong solutions, we get this entropy conservation equation. But I should stress that what we mathematically call entropy for the isentropic Euler equations is in fact the energy. Okay, and now when we talk about weak solutions, we want to have the second law of thermodynamics, which essentially means that well, there is only a balance for the entropy, and entropy in this setting is required to be non-increasing. So it's a convex function, so it's just the other sign convention as in physics. So here it's something convex, which is decreasing. In physics, you would want to have something which is concave and increasing. Okay, once you have this convex, or indeed I would like to have strictly convex entropy, if you have two states, you can of course look at all kinds of metrics to measure the distance between the spaces, and one particular way to measure the distance is the so-called relative entropy. It's also sometimes called Brakman distance, and it's in some sense the quadratic part of a Taylor expansion. So we look at the entropy at q minus the first order Taylor expansion of the entropy around q bar. So when we write the error term, there is some intermediate point q tilde. So this is q minus q bar times Hessian of eta at q tilde, q minus q bar. So in a strictly convex setting, that's essentially, I mean, in a weighted way, but in some sense controlling the relative entropy is controlling up to this weight the squared L2 distance. But what I should stress, of course, is that this is not a metric in the standard sense, because this expression here is non-symmetric in q and q bar. So you can't just take the square root and say this is a metric. but still it's a nice way to, or it's a way to measure distances, albeit non-symmetric. But why is it useful? Well, it's useful because one can actually show that if Q is an entropy solution and Q bar is an entropy solution which has the additional property of being Lipschitz continuous, which is of course a very strong requirement, then there is a balance inequality. So the time derivative of the relative entropy plus a relative entropy flux, which won't really matter because we consider periodic boundary conditions, so this goes away upon integration, has a right-hand side. And here we really see that Q bar needs to be Lipschitz continuous because, well, I mean, we need to talk about weak derivative, or we need to talk about derivatives of dq eta at Q bar, and this is multiplied by this relative flux, which is defined here. And now the way the story goes is the following. So we assume, as I said, that Q bar is Lipschitz continuous. So this derivative here is essentially an L infinity function. And the relative flux between Q and Q bar is quadratic. And the relative entropy is something, again, quadratic, but with a positive sign. So essentially, up to a constant, we can bound the relative flux, or the absolute value of the relative flux, by the relative entropy. And then we can use Grunwald's lemma. And what we see is that the relative entropy at a given time between these two solutions is bounded by a constant times the relative entropy at the very beginning times this exponential factor. And in the exponential factor, okay, this shouldn't be a derivative, but a gradient. But I mean, the philosophy is clear. So the steeper gradients Q bar has, the less strong this stability result is. And in any case, I mean, we have this exponential growth term here. On the first glance, this is not a particularly great stability result. In particular, it doesn't allow us to compare two entropy solutions. It only allows us to compare one entropy solution and one Lipschitz continuous solutions. And at least I myself for a long time thought, okay, there should be a better result which allows us to compare two entropy solutions. But for the last 10 years, there are results by the Lellis and Székely-Hidi, which I would say originated in the incompressible world, but then can be extended very easily to compressible problems where they use convex integration techniques to construct so-called wild solutions. And they can show that essentially for generic initial data, there are several entropy solutions once a shock forms. So some of the philosophy is that you start from smooth initial data. For some time, the data remains smooth. Then a shock forms. And then suddenly, at least in multi-D, you have a plethora of solutions. And so essentially, there are also proof techniques via the Baire category theorem. So there's really lots and lots of solutions. It's not. It's like 5, and you can somehow start looking at them individually. OK, so but in some sense here, I mean, that's really the best we can do. And although this is not much, we thought it would be nice to essentially see how this methodology and how this type of stability results carries over to these more general systems of this form I showed in the very beginning of my talk. OK, so the first thing we wanted to do was to try to extend the notion of relative entropy. And actually what we did was splitting things into a potential energy part, where here somehow all the interesting stuff happens to a certain extent, and the kinetic energy part, which is the same for all the models. So I mean, the E of rho, so this potential energy function, is really where the different models differ. And OK, so again, I mean, here we evaluate the generator of the derivative of the energy on this difference. So again, it's essentially the quadratic part of the Taylor expansion. And at least formally, we can show that the time derivative of this is something like this, which again depends on derivatives of the smooth of the Lipschitz continuous of the two solutions times this so-called relative stress, which again has this standard part. And here we have something which looks a little bit strange, but it's not so bad, because once we look at the kinetic energy, so I mean, there you do the same thing. You look at the quadratic part of a Taylor expansion. It's a bit messy because now things depend on momentum and density. So figuring this out, well, I mean, it's not complicated, but it takes like half a page because everything is just lengthy. You go through the analysis again. I wouldn't say it's difficult. Well, the difficult thing is not to fall asleep and forget terms. But at the end of the day, you're here, at least on a formal level. You add things up, and you have this, I would say, fairly clean formula. The very nice thing is here you have a row in front of this velocity differences. So this term can be very easily bounded by this term. And somehow what you need to check is whether the relative potential energy is enough to bound the relative stress. And that can be a little bit complicated. The other thing is, I mean, these computations are very, very easy on the formal level when I assume everything is smooth and I can do everything I want to do. De facto, I mean, what we want to have is this weak, strong uniqueness. So we de facto don't want to assume the rho and m to be smooth. And then actually to make sense of all these computations on the weak level, that's, I would say, a little bit more of work than the formal computation. Yeah?
Did you derive the energy equation for second order material, so for posteriori equations? In the energy equation, there is the term called interstitial water.
Yes.
It's completely new compared with earlier equations. I don't see where it is, this term. I mean, when you roll this relative entropy, it doesn't work or what? I mean,
it works very nicely.
Okay, it disappears finally, yes?
Essentially, yes. I mean, there is also this, in some sense, new derivation of these things by Kotschote and Heinrich Freistühler, and they have a different interpretation. So from my perspective, I mean, there is this Dunn-Ansarian view on things, and they have this interstitial work. But from my perspective, I mean, everything fits very much into the structure which is there. So. The only tricky part is, and this is why I showed this reformulation of the stress, is that on the first glance you might think that here you have differences of second derivatives of densities. And this, of course, you would not be able to control with this, because this only controls differences of first weak derivatives. But some of the trick is that you can throw another derivative onto this test function. So what we will de facto need is that this is not only Lipschitz continuous, but this needs to have bounded second derivatives. But then things seem to be fine. OK, and so for strong solutions, that's what I showed. And for dissipative weak solutions, this is what we have. And OK, since everybody was showing lots and lots of function spaces, I added a slide this morning with lots and lots of function spaces. So essentially what we need in terms of regularity is, yeah. I mean, this here, and in particular, yeah, we need to have first derivatives of rho being in L2 or the square being in L1. We don't really need second derivatives on the level of weak solutions. And we need this decay property for the entropy. So here we have some test function, which, because we're working with periodic boundary conditions, we don't have to make space dependent. And here's the time derivative, and we assume that this function is 0 when time goes to 0 when time goes to infinity. OK. So when we wrote this paper together with Corrado, we wanted to have a clean and nice theory. And lots of problems go away if you have as a local part of the energy density rho to the gamma. So we picked rho to the gamma. And then we can define this phi of t, which is essentially the relative entropy between the two solutions at time t. And we can show that the relative entropy at time t is bounded by a constant times relative entropy at time 0. Of course, as before, the constant depends on properties of this solution rho bar u bar. And it grows exponentially in time. So this is really only finite time stability, and in some sense this also means we have weak strong uniqueness on the level for the Euler-Korteweg system. And from my point of view, I mean, there are some works around where people somehow treat this term as something which is, I don't know, annoying and needs to be dealt with, and actually this helps in the analysis, I would say, or at least it helps us to get control in nicer norms. What I would also like to stress is that this is really in no way a perturbative theory, so it gives us stability results independent of the initial difference between the solutions. So it's not like data have to be small in any way. Okay, when I started working on Navier-Stokes Korteweg, my main motivation was to look at multiphase flows. And in multiphase flows, what happens is that in the pure phases, the pressure is monotonely increasing function of the density. But when you go from one phase to the other phase, the pressure actually goes down, or in other words, the energy density is a non-convex function. So a typical van der Waals energy isotherm close to the critical point would look like this. So we have this convex part, and densities in this area we would kind of identify as vapor. Then we have this intermediate region in between where it's not so clear what it means physically. And we have this liquid part over here. So yeah, so the energy is definitely not convex, and that kind of changes the complete ball game, because in the very beginning, I mean, what we did was bounding the relative stress with the relative potential energy. And the relative potential energy is only something positive, being proportional to the square of the distance, provided the energy is strictly convex. And strict convexity is certainly gone here. But so what we tried to consider was a situation where we have this rho to the gamma, which we again used because it's nice, not because it's particularly realistic for this case. And we have some perturbation in the energy density, which has a support which is localized. So it neither appears for very small densities nor for very large densities. And I mean, in some sense, you can view this as a decomposition where we say, okay, we have a convex part, and then in the middle, there's like a bump added to everything to make it non-convex in a certain isolated region of density space. And then the trick is to define a functional which is now the relative entropy, but ignoring the things coming from E. And of course, we can't directly show anything for this. I mean, we can only show things for the proper relative energy, but the trick is really to say, okay, this is lower order. These are the leading order terms in the energy and everywhere. And okay, this is not the order I want to go. Okay, this is what I want to go. So in some sense, we need to remove this relative energy with respect to E part from the whole relative energy. And well, essentially the reason why we can do this is that this is indeed lower order. We compute things, we use conservation of mass, and we use the fact that we can actually control differences of gradients of densities, because the gradient difference is part of the relative energy because of these capillarity terms. So we can control this. We get more terms on the right-hand side. And then at the end of the day, yeah, for this phi, which ignores the contributions from E, so which only sees the convex part, what we get is indeed a stability estimate which looks essentially the same as before, but it's really not exactly the same as before. And I mean, what happened before was that the constant depended on the smooth solution and on the final time. But what happens here is that we essentially use terms in the energy which scale with kappa to bound differences which don't scale with kappa. And in this way, we cannot avoid having a kappa dependence of the constants. And the kappa dependence is really bad in the sense that the dependence is like exponential of 1 over kappa. So this is certainly not what we want. I mean, I don't know, from a pure analysis point of view, my feeling is okay, kappa is positive, so it's a positive constant, but at least for the numerics, I mean, that's terrible. I mean, in the numerical scheme, I don't want to have a bound which tells me, okay, the error is smaller than 10 million. It's not a very good selling point. Okay. I certainly need to speed up. Okay, so one application of this whole methodology would be to look at the large friction limits. So this is Euler-Korteweg again, but now we have a friction term here. It's linear friction. And we rescale time, so we have 1 over epsilons here, and we have a 1 over epsilon square in the friction term. On a formal level, we could insert Hilbert expansions. Well, then if we look at the leading order terms, well, the leading order here is that the divergence of m0 is 0. Here the leading order is that m0 is 0. So m0 is certainly 0, and then this guy vanishes. In the next order, here we get the time derivative of rho 0 balances with the divergence of m1. Well, in the next order here, this is the 1 over epsilon order. So we have this with m0s and rho 0s. So this goes away because we know that m0 is 0. We have this with an m1, and we have this with lots of rho 0s. So as I said, this is 0, so we can identify m1 by this expression only involving rho 0. We can insert this here. And what we see is that rho 0, at least formally, satisfies the Cahn-Hilliard equation with variable mobility, where the mobility is proportional to the density. Okay, and now the goal was to make this convergence rigorous using relative entropy. So we start with a solution rho bar of Cahn-Hilliard, which is nice and smooth. And then we define an m bar in this way, which I should stress contains an epsilon. So m bar is actually small for epsilon being small. We insert this into the large friction Navier-Stokes equations. The right-hand side here is 0 by construction. This is essentially the construction principle of m bar. And we use, of course, the fact that rho bar solves the Cahn-Hilliard equation. And the interesting phenomenon is that, okay, you could be afraid that there are lots of 1 over epsilon terms surviving here, but indeed, the error term here is of the order epsilon. So this is really for epsilon small, a small perturbation of Euler-Korteweg with large friction. We can crank the machine, do relative entropy, and now keep track of the effects of this additional E bar and of all the epsilons. Well, again, we have relative kinetic energy. We have this local part. We have the capillarity part. And what we see is that the essential difference is that we get this epsilon to the 4 term, which is essentially the consequence of some of the epsilons flying around, in particular this E bar term, which means that if the initial data are such that the initial difference between the difference in this metric between the initial data goes to 0 for epsilon to 0, then indeed for any finite time we have convergence of the solutions of the two models towards each other. But of course, this methodology only works as long as the limiting Cahn-Hilliard equation has a rather strong solution, or a rather smooth solution, I should say. And as before, in the non-convex case, of course, these constants showing up here will depend not only on final time and stuff like this, but also on the capillarity parameter, kappa. Okay. I've been working quite a lot on numerical analysis in the last years, and I'd like to use, I don't know, 5 or 6 minutes to try to explain a link between this stability analysis on the PDE level and numerical analysis. And to do this, I'd like to consider a toy problem. So it's not really what we had before in Lagrangian coordinates, but in some sense you can make sense of this as a 1D elastodynamics model in Lagrangian coordinates. So U now is the specific volume, V is the velocity, and tau is this variation of the energy function. I have included viscosity here, but actually you can just think of the case that mu is 0. So if you have viscosity, it helps a little bit. If you don't have viscosity, it's still fine. Okay, the Hamiltonian is potential energy W 1 over v squared in this capillarity term. So I mean, this is really a toy model. I'm not claiming that this model makes a huge amount of sense from the physical viewpoint. I mean, the nice thing about this model is in some sense that it tends to be, in some sense, it's a little bit more linear. Because somehow here we have directly the derivative of the energy, and it's not this pressure function related to things via Gibbs to him. So, but essentially, I mean, we have a similar Hamiltonian structure, and we have an energy function which contains this non-convex local part, and then it has this convex or this quadratic gradient part, which should help somehow. Okay, and yeah, I mean, I want to use the stability analysis to say something about numerical schemes. So I should say maybe a few words about which schemes we consider, and what schemes we consider are so-called discontinuous Galerkin schemes. So the first thing we do is we discretize the computational domain. So we just chuck our interval into smaller subintervals. And then at any time, we look for the solution in the space of piecewise polynomials. So this VP is the space of functions whose restriction on every of these subintervals is a polynomial of a given maximal degree. Okay, and then we need to somehow say, okay, how are these degrees of freedom of these polynomials evolving? And the idea is to say, okay, we take a test function, which again is a piecewise polynomial on the same subintervals. We multiply the equation, for example, the first one by this test function. We integrate by parts. And what happens is that we have these boundary terms. And now the first thing you could say is, oh, I do this on this interval, so maybe it would be a good idea to just take traces from the inside. I mean, in that sense, it would be mathematically correct. The problem with this is that if you do that, the subintervals don't talk to each other. So that obviously doesn't make sense. I mean, the subintervals need to talk to each other. I mean, otherwise we're just solving evolution equations on very, very small parts of the domain which don't see each other. That doesn't make any sense. Well, so essentially what we need to do is, for the test function, we can use traces from the inside. But for our solution, we need to choose information from the outside. And the interesting thing is for this model that it's enough to use in this equation information from the one side, and in the other equation to use information from the other side. And together, that's enough to transport information in both directions. I'm not claiming that this is always the case, but I mean, there is an analysis for things like the wave equation, which shows that this is fine. So okay, we have the product of our ansatz u times this test function is velocity times derivative of the test function, and then on the edges, so essentially on the points between the intervals, we have the trace of the velocity from the right times the jump of the test function. Okay, and we also need to discretize the Laplacian, and what we do is this so-called symmetric interior penalty discrete Laplacian, and the nice thing is that this is a symmetric positive definite bilinear form if we choose parameters in a good way. If anybody wants to talk about this in detail, I'm happy to talk about this in detail, but I don't think this is the proper conference to talk about this in detail. Okay, at the end of the day, we have a semi-discrete scheme, which in some sense is nothing but a huge system of ODEs on this space of piecewise polynomials, and then we can use some, I don't know, Runge-Kutta or whatever scheme to discretize this in space, but okay, to explain what I want to explain, I think it's nicer to just stick with this semi-discrete level. And one thing which is relatively easy is showing that if there is a smooth solution, or if there is a C1 solution of the system of ODEs, then this solution satisfies an energy dissipation equality, or if mu is 0, it conserves energy on this discrete level. So here it's no longer the gradient squared, but this is using this discrete version of the Laplacian to measure the capillary part of the energy. And what I want to talk about is how to come up with an a posteriori error estimate. This is an upper bound for the discretization error that we can compute from the numerical solution itself. So the assumption is really we solve this, and then from the numerical solution we want to know how bad can the numerical solution be. And okay, the basic idea is, and this is the link to the first part of the talk, where the standard idea is to insert the numerical solution into the PDE, and then use PDE stability to relate the residual to the error. This is very similar to what we did in the large friction limit. Of course, now the problem is the numerical solution is not at all smooth enough to do this. So what we need to do is the so-called reconstruction. So essentially from the numerical solution we compute something which has more regularity. I don't think there's enough time to go into any details. And okay, once we have more regularity, we can crank the handle. We can relate the residual to the error. It's not just as simple as that, unfortunately. That would be very nice. But we have to be very careful in how we perform these reconstructions. It has to be done in a very, very smart way related to the numerical scheme. Otherwise, we still get an upper bound, but we get a bound which crazily overestimates the error. So essentially what we want is that if the error goes down like h to the power, I don't know, 5, then the error estimator, so the bound we have, should also go down like h to the 5 and not like h to the 3. And this requires to be very, very careful with the reconstruction. So I don't think I should go into any details anymore. I'd like to come to the summary. So we've extended this relative energy framework to a rather large class of models, which has this Hamiltonian or kind of Hamiltonian structure. And I think this is a nice tool for doing lots of things, in particular studying things like large friction limits or weak strong uniqueness, but also it's a nice tool for performing numerical analysis. What is also interesting is that essentially we don't really need the energy to be convex. We only need, in some sense, convexity somehow in the leading order terms. So non-convexity in the not leading order terms we can deal with, but the price is that somehow we get parameters into the estimates, and we run into trouble if these parameters, depending on what they are precisely, go to 0 or go to infinity. When I decided to come here, I was really, really optimistic that I could show better results, because we've been working a lot on trying to obtain bounds which are not so sensitive with respect to kappa, but unfortunately we're a little bit stuck there. So I'm sorry for not being able to present you really new results. And with this, I'd like to thank you for your attention.
Are there some questions? Are there some questions? Okay, I don't really understood why you need the entropy inequality for Euler-Korteweg system. Because when you have hyperbolic equations,
Yes.
initial data are smooth, then simulated in ULP, you need inequality. Okay, understand perfectly. But when you have Euler-Korteweg system, have smooth initial data, solution will stay smooth because you have dispersive regularization. So inequality will be equality, just energy will be conserved. So I don't understand why you need inequality.
I mean, essentially, it works for any weak solution. Okay, actually, I don't know. I think there are people in this room who might know this better than me. So it's not so clear to me in Euler-Korteweg whether I really have long time existence of smooth solutions.
I mean,
Well, it's not so clear. I mean, I think there was a similar discussion this morning that it's not so clear. Yeah.
There's no theory, but I mean,
Okay.
no hope to have such a solution.
Okay, let me put it this way. So, I mean, it works for strong solutions, and it also works for weak solutions as long as they satisfy this entropy inequality.
Yeah.
So, I don't know whether...
It's formal. I mean, we don't know exactly what kind of mixed
Yeah.
solution will appear.
So, I mean, I don't know. I mean, somehow as a mathematician, I would like to have this stability result for as large a class of solutions as possible. And from my perspective, that's the largest class we can make sense of at the moment.
Is there another question?
Yes, my question was also about the existence of global solutions. I don't know if you can say a word about it.
I can't say anything intelligent about this.
So I had a question about the first part of your talk when you say about generalization of the results. And I understand the use of growth bar gamma in the situation when your energy entropy is non-convex. But what about the use of this growth bar gamma in case you don't have, assume that you have some convex function there on the right hand side. So for example, Athanasios Tzavaras, they are considering often this non-local interactions on the right hand side. Let's say that you have something like Poisson term over there.
Yeah, so for the Poisson, everything works. So, yeah, so, okay, I don't know how to really phrase this in mathematics. No, wrong direction. Okay, so the crucial question is somehow how to estimate the relative stress using the potential relative energy. And in the Poisson term, this works perfectly fine, no matter what the sign is actually. Because again, there is this argument that we only need convexity in the leading order terms. If the right-hand side is, I don't know, truly nonlinear in the sense that the only way we can write it is like convolution with some kernel, then it's currently unclear to me how to bound the relative stress with the relative potential energy. So that's really the bottleneck. So for
Even if you have some stronger singularity in the region than just
so my feeling is that everything is fine where I can write the equation for C as an elliptic PDE. So it could be by Laplace or anything like that. But I stop seeing any structure if I can just write it as a convolution. But my understanding was that Yongpil Choi has some results in this direction, but I haven't really looked at them in detail, so I can't properly say what it is.
Okay, let's thank again the speaker.